theoretical models, okay, that could generate complex networks that will resemble like real world networks. So far we have seen more real world networks, right? So for assignment 1, each of you got some real world network that you're analyzing. So what we are going to see is how to generate some networks whose characteristics or properties or values for some metrics would be similar to those that we get in real world networks. Okay. So we are going to kind of also, by using these models, try to design whether the nature of the links. One very broad categorization would be whether the links in the network are just appearing in random. So if you put like 10 people together and you say, okay, this is a network of these 10 people, okay, who is talking to who? Do they talk just randomly to one of the other person, or they prefer to talk to some person? Okay, so accordingly we could have, say, random networks where there is no preference for a link between any two people or any two nodes. They are just randomly created, okay, or coming out. Whereas we have scale-free networks where there's a preference for attachment or preference for a link. So one user may be very famous and everybody will be talking to that person, whereas some other people who are not that famous don't have any link. Okay, the airport network is also a scale-free network because we have some airports that are like a hub where a lot of connections will be there, whereas some other airport will not be a hub, like Jackson Airport is a small airport with very few connections and so on. Okay, whereas Atlanta is a very big airport. So we have scale-free networks that model this preferential attachment. So we can kind of characterize the real-world networks to be either random or scale-free, okay, by comparing some of the properties or values that we get with the theoretical models. So as we proceed to this module, we'll see how to do all this. Okay. So there are three broad models, categories of models we're going to see: random networks, scale-free networks, and small world networks. We'll see one by one. Okay. Okay. So random network. So as I said, a random network is a network in which there's no preferential attachment. So if you put like 10 nodes, there is just a probability for a link between any two nodes. We cannot say for sure that there is a link between two nodes. There's only a probability for a link between any two nodes. So based on this, if you generate a network, such a network would be called a random network. Okay? And there's a well-known model called the Erdos-Renoi model, just the name of the people who came up with this. So we'll call this as the ER model. And it can be also referred to as a GNP model. So G refers to graph, and N for the number of nodes, and P for the probability or the P link.
So ER model is like what it is?
No, not in the database.
Yeah.
No.
When I saw that, I thought, I guess.
No, that is not. That has nothing to do with the database ER model.
Yeah.
Okay. This is just the name of the people. I think their ER means what?
It's
Entity.
Entity and relationship.
Right. Okay. So it doesn't stand for Erdos-Renoi. All right. So G. It can be also referred to as GNP model, where G means graph, N for the number of nodes, and P for the probability. So I can say G of 10, 0.2 means it's a graph of 10 nodes, where the probability for a link between any two nodes is 0.2. Okay. So how to generate such a graph? So let us just take an example like this. So I want to generate, say in this case, a graph of 8 nodes, a random network of 8 nodes, and 0.524 is the probability for a link between any two nodes. Okay. So how to generate something like that? Okay, so the procedure is write down all pairs of vertices. Okay, so if we have 8 vertices running from 0 through 7, no, it's not 8, 7 vertices, right? Okay. So graph of 7 vertices, 0 through 7, 0 through 6. So 0, 1, 0, 2 up to 0, 6, then 1, 2, 1, 3 up to 1, 6, and so on up to 5, 6. So for each pair, generate a random number, okay, between 0 to 1, right? So if the random number or random value that you generate for that pair is less than or equal to this p-link, the probability, then there is an edge between the two vertices that are the pair, okay? So for example, the random number here is less than 0.524. So there is an edge between 0 and 3. So I say yes, there's an edge between them. If the random number that you generate is greater than that p-link, the p-value, then there is no edge between them. Is that clear? So as you can see, it's a probability. So I get a network based on the random values I generate.
So can you please explain again?
Yes. So I write down all pairs, and for each pair just generate a random number, from 0 to 1.
What number?
Random value. Have you generated random numbers? You know what a random number is?
Yeah.
So use a random number generator and generate random numbers between 0 to 1. Okay? And if the random number that you generate is less than or equal to the p-link value for a p-link means probability for a link between any two nodes according to the model. So that is given to you. Okay? So I want to generate a random network of 7 nodes such that the probability for a link between any two nodes is the specific value, like 0.524. So if the random number that you generate is less than or equal to this p-link value, then you say there's an edge between them, otherwise no. So you may realize by now, the graph that you generate depends on the random numbers that you generate. If I just generate another set of random numbers, I may not most likely generate the same random number for this pair. I may generate some other number, say 0.7, that will be greater than 0.524. So if I generate another set of random numbers, I may not get the same graph. I may get some other graph of 7 vertices with some edges. Is that clear? So that's the nature of random networks. So like I show here, this is a graph of what? Some 10 vertices, 1, 2, 3, 4, 5, 6, yeah, not 12, okay? So same number of vertices, but each time, and the p-value is also the same. But each time I generate the random numbers for every pair, I would end up with this graph or this graph or this graph. The number of edges could vary in those instances. But all these are random networks with the same number of nodes and same p-value. Okay, so that's why when, okay, it's given here, n is 12 nodes and p is 1 over 6. So that's the value, 12 nodes, and the probability for link between any two nodes is 1 over 6. Okay? So if you want to get some property, more likely you have to average out the results. Okay? By generating several random graphs with the same n and p value, and then average out, say for example, average clustering coefficient or average degree or so on. Okay? So similarly, this is a random network of 100 nodes with 1 over 6 as the p-link value. Okay. Now, so
that random value we will means we will generate through Java file.
Yeah, you could use Excel to generate. So in an exam, if I ask you to do something like this, you could use Excel. Yeah, to generate random numbers in Excel. Let me show it here. Okay, there's a function called equals randoff, so you can say equals rand. Okay, so you can open Excel and type equals rand and something like that, empty parenthesis, press enter. So it will generate a random number from 0 to 1. Okay. Now, if you want to generate say 10 random numbers, you can copy and paste it.
Okay.
But the thing is, the random number that was generated before will go off. So each time you generate, you click on that cell, on that use that formula and generate a random number, the whole sequence will change. Doesn't matter, they're still random numbers. Okay? So if I want to generate one more random number, I press Ctrl V because I copied that formula. So I press Ctrl V here to get another random number, but the whole thing will change.
Why, sir?
That's an Excel feature. So because you're using the formula from the earlier cell. So and that one is generated from the previous cell and so on, so the whole thing will change. Doesn't matter, all you need is random numbers. Okay? So generate that many random numbers depending on the number of pairs you have. Is that clear now? Okay. So once you have a graph, once you decided which pair is having an edge between them, linked between and not having an edge between them, then you can draw a graph and determine everything you want. So you can determine, say, the average degree, which is the sum of all the degree values divided by the number of vertices. Okay. Now,
So that random value we have like anything, right? Just put it and just write it.
Right. Now, so the P link, the probability for a link could range anywhere from 0 to 1. The probability always from 0 to 1. Now, what does it mean if I say P link is 0? If I say P link is 0, it means the probability for an edge between any two vertices is 0. Then would there be an edge at all between any two vertices? No, right? So all the random numbers that you generate would be greater than 0, P link, right? So that is why if P link is 0, there is no edge between any two vertices. On the other hand, if P link is 1, all the random numbers that you generate will be less than or equal to 1. So which means there is going to be an edge between any two vertices. So if P link is 1, you're going to get a complete graph. Complete graph means edge between any two vertices. Okay? Is that clear? Now let us go ahead and determine or do some theoretical analysis.
Sir, if it's 1, then no one will come under it, right?
You're partly sleeping. What did I say? If P link is 1, then there's an edge between any two vertices. Because all the random numbers that are generated will be less than or equal to 1. Because random numbers are going to be between 0 to 1. So it means if the random numbers are less than or equal to P link, is there an edge or not between any two vertices? What is the model? All these random numbers are going to be less than or equal to 1.
Yes.
So if that is the case, is there going to have an edge between any two vertices or no edge? What is the model? If the random number is less than or equal to the P link value, there is an edge between two vertices, the pair.
Less than or equal to.
Okay? So which means if P link is 1, you're going to have an edge between any two vertices. That will give you a complete graph. Only if it's greater than P link, there's no link.
Yeah.
Okay? Right? Any question? Okay. So think about it. So for a particular vertex, what is the maximum number of edges it can have if there are n vertices or n nodes? How many edges there can be for a particular vertex? We have n vertices, n nodes, right? Just pick a node. What could be its maximum degree?
N minus 1.
N minus 1. Good. So it could be connected at most to n minus 1 vertices, right? And according to our random theory model, the ER model, there is always only a probability for a link between any two vertices, right? So n minus 1 could be the maximum degree for any vertex, or the maximum of edges incident on any vertex. But each of those edges could be there only with a probability p link, right? So n minus 1 times p link is what is called the expected or average degree. You know, from statistics, average degree, average of something can also be called expected value, right? So this is the simple formula for the average degree according to the ER model. Okay, so if there is always only a probability for a link between any two nodes, then the average degree can be theoretically estimated, okay, as n minus 1 times p link. Right. Now, then you may wonder, for this random network that we generated here, okay, according to the ER model, because this was generated according to this ER model, we could estimate what would be the average degree for this network. How? We know it is a graph of 7 vertices, and so the average degree is going to be 7 minus 1 times the 0.524, the p-link value. So 6 times 0.524, what do you get? It will be some 3.3 something. Okay, so you are more likely not to get the same as your average degree that you have from on the graph, because as I said, this is the average degree provided the edges are distributed like this. If you run another instance of your random number generator with different random numbers, you could get a different network of 7 nodes with edges. So if you find the average degree for that network, it will be 3.6 or 3.8. Okay, so that's why you have there are two things behind this. So for a smaller graph like 6 or 7 vertices, the average degree that you get out of an experiment will more likely not match your theoretical expected value. So you have to really try on a larger network, I'll show a little later, to really match the theory with what you get in practice. The other thing is, if you really also, if you work with larger nodes, you cannot just try with one network. You have to create several instances of the random network and then average out the results. So you have to find average degree for several random networks of 100 nodes and the p-link value, and then average out the results. Okay, so that's what I showed here. Okay. So in the first module, partly we saw how to get the degree distribution. Does anyone remember that now? You also probably did for exam 1, right? So we saw how to get this K versus PK distribution. Do you remember that? Given a graph, find the number of vertices with each degree value and then count the number of vertices and divide by total number of vertices, and you plot the K versus PK. So if I do that for the random network of, say, here I have 100 nodes and the p-link is 0.1. Okay, so I created a random network based on the procedure which I just explained. Just write down all pairs, generate random numbers. If it's less than or equal to 0.1, there's an edge between them, and so on. I created several such network of 100 nodes and averaged out all and found the degree distribution. Okay, so how many nodes are degree 1, how many are degree 2, and so on. So the degree distribution came out like the red curve, okay, according to the ER model. So clear? So for random network of 100 nodes with the p-link 0.1, it came out to be like this. Okay. Now, is this shape familiar? Again, in module 1, I said we'll come back and look at the shape and distribution later. So that now it's the time to see this. So this shape corresponds to what? Poisson distribution. Okay, so Poisson distribution is just like one of the distributions in statistics of how the data gets distributed. Which means the degree distribution of the random network generated according to the ER model is very close to a Poisson distribution. Okay. Now, as I said, if n and p link are given to you, the average degree is n minus 1 times p link. Now, do you know how to generate a Poisson distribution data? You have seen in any math class here. There is a simple formula. The probability, so we are dealing with degree here, right? So the probability of finding a node with degree k is going to be e to the power minus average degree times the average degree raised to k divided by k factorial. So if you are given the average degree, you can generate the Poisson, the k versus pk value for a Poisson distribution. Okay, and we can plot the k versus pk values. So let me show again the Excel how I did it. You can try it. So let us say n is 10 and p is 0.3. So according to our ER model, the expected or average degree is n minus 1 times p. So which is our average degree, so it comes out to be 2.7. So using this 2.7 as the average degree, we can generate, what is that, e to the power negative k the p versus k versus pk distribution. So all you have to do is okay, so write down some k values starting from 0. You can go to even larger than 10, but we'll see when to stop to get an idea. Then e to the power of negative average degree. So average degree is given to you is 2.7. So e to the power of negative 2.7 is the same value for all the entries. Then the average degree 2.7 rise to the k value. So 2.7 rise to 0 is 1. 2.7 rise to 1 is 2.7, 2.7 rise to 2 is this 7.29 and so on. Okay?
So on what value, that is k to the power k?
Average degree rise to k.
2.7
Average degree is 2.7.
on k.
K is this. K is
okay.
K is a variable.
Yeah.
Okay? Then k factorial. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 and so on.
No, over there there are two k's, right?
This is average degree. If I just put k like this as a variable, it could take different values. This is a constant. Average degree is just one value.
Yeah.
Okay? So now put everything together. The pk probability, what is the formula? E to the power negative average degree times average degree raised to k divided by k factorial. So you have to just multiply these two column values divided by this column value. So that will get you the last column, the probability. So now you could plot the k values 0 through 10 with this probability values pk. So you will get a curve like this. So this is how a Poisson curve will look like, right? So why you can stop at 10? Because after 10 it's very negligible. So 0.000, it will go on. It will be not like 0. It will be like 0.0001, 2 and so on. Okay. Now the average degree is the peak of the Poisson curve. So that's a property. So that's going to be like, if you kind of draw it down, so that's going to be close to 2.7. Okay, so the peak of the Poisson curve is the average of what are the parameters parameter here. Our parameter is a degree. So you can try it like that as a practice. And I have one more network. So if n is 10 but p is 0.7, it's just that the distribution will be skewed towards the right. Okay, so it will be towards the right because the average is now p is 0.7. So 0.7 times 9 is going to be 6.3. So it will look like this. Okay, so that is how I can generate
So
now.
what is P you say?
The probability for an edge.
Okay.
Now see here, pk is probability for observing a node with a certain degree. K. So what's the probability of finding a node with degree 2? Or you did that in the first module. Remember, I gave you a small graph. You found the k which is pk. So that's the same thing I'm talking about. Okay. So now you can get a feel of how I got the green line. How? Because I said this is a network of 100 nodes with a p-link value of what? 0.1. So what is going to be the average degree?
100 minus.
Average degree is going to be 100 minus 1 times 0.1. So that's going to be 9.9. So using 9.9 as my average degree here, for different k values, I found the pk values and plotted the green line. So that's the Poisson distribution. And this distribution matches very well to the distribution that you get with the ER model. So how we got the ER model distribution? Just generate the random numbers for every pair of vertices, the range 0 to 99, and then draw the graph and find how many vertices have degree 1, how many have degree 2, and so on, like you did in the exam earlier. So that will lead you to the red line. So they both match, they are the same. Okay? So which means that the degree distribution of the random network generated according to the ER model will exhibit a Poisson distribution, or will be Poisson in nature. Okay?
So Poisson is understood, ER model.
That's what we are seeing from the beginning, ER model. You also said is it entity relation model, right? No, this is endosynthetic model.
I got it, that random okay, you need to put random number and you need to pick through the random number. You need
That's
to
the ER model.
Okay. You need to make a graph on with that and random number.
So make a graph with the random number, it is depending on whether you have an edge between them or not. So for that graph that you got here, you could find what? The degree distribution. Okay? Alright. Now, what is something you can talk about Poisson distribution? One thing is the standard deviation. Have you heard of standard deviation? Okay. So it's a measure of variation in degree. If you have not heard of standard deviation, there's a mathematical formula to find it. If we get time later, I'll show you how to do it. But how many of you know how to find standard deviation using the math formula? 1, 2, 3. Okay. No? Yes? Yes? Okay. Let me see if we have time today. Let me show it so that we get a feel of it, otherwise we keep on talking standard deviation. Oops. Good save. Very important. Okay, so I'm showing now, so if later you need to know how to do it, you should be able to do it, okay? Alright, so let us use the small graph that we got here. So let us first write the k values. So what are the k degree values here? Does any node have degree 1? Any has degree 1. Got a count. So I'm just finding the pk values first. Anyone with degree k? 1? No. Okay. What about 2? 0 has degree 2. Anything else? So 1 no. How about degree 3? 1, 2, degree 4. 1, 2, 3, 4. 5, I think 4 has 5. Right, so we already have 7 nodes. You have more than 7.
It's
C1.
It should be, yeah, 3 should be only
Three should
one.
be
There's only one node
Yeah.
in degree 3. Which
so-
one is that? 2.
Oh,
Okay, so this is our distribution, right? Yes? Okay, so this is a count. So there's no node with degree 6 or no node with degree 5 or degree 1. So remove this. So we can get the pk values right away. So what are they? So the value here v2 divided by the number of nodes 7. So these are the pk values. Okay?
pk random.
The count divided by the number of vertices. This is how you did before. The number of vertices with a specific degree divided by the number of nodes. That will give you the probability. Huh?
That's the peak level.
Yeah, for this degree.
pk.
pk, the actual pk values for this graph.
Okay, and minus 1 into.
Not that.
It's the
pk is the
count.
probability of finding a node with a certain degree.
It's the count divided by the total number of nodes.
Count the number of nodes. Remember we did in the first module. Given a graph like this, count how many nodes are degree 1, how many are degree 2.
Yeah.
Yeah, that's the pk value I'm talking about.
Okay.
Okay? So 1 divided by the number of nodes is this. So that's the probability of finding a node with degree 2. Probability of finding a node degree 3 in this graph.
Yeah.
Okay? Now, using this, we can now also find what? What is the formula for average degree based on this? So average degree can be found different ways. One way is just find k times pk. So k times pk is going to be a2 times c2. So that is k times pk. So find all the k times pk values. The sum of k times pk is going to be the average degree. So this 3.714 which I show here is the average degree. And we did also like this, the first module. Okay? Summation of k times pk. So that's the average degree. So now how to find standard deviation? I may have here also somewhere. Let me check. Yeah. So this is the formula for standard deviation. Now for average, k times pk, sum of all the k times pk is the average degree. For standard deviation, the formula is k minus the average degree, the difference, squared times pk. Okay? So which means what we're going to do? We found the average degree to be this number. Right? So now we have to find what? So I can say this is k times pk. So now what we have to find? K minus the average degree, right? Square. That's the formula for standard deviation. So square that. So that's going to be like what? K is our VA2, the number K, right? Minus the average degree 3.714. So you can use this level of precision. Square. So time raised to 2. So that's going to get K minus the average degree square. Then just copy and paste this formula here, okay? And then what you have to do, according to the formula, it is k minus average degree square multiplied by pk. So we have to multiply this column. So we have to find what? K minus average degree square times pk. Okay? So what do you have to do? E2, this cell multiplied by C2. So multiply, and then what's the formula? Add all those things. So sum of all these values, F2 to F5. So that's going to be a standard deviation.
The square root.
Good. Square root of that. Okay. So if I just leave it like that, it's called variance. That's another name. Okay. So if you take a square root of this, it's going to be called standard deviation. Okay. So what's the purpose of computing the average and standard deviation? We can say the range of degree values is going to be the average plus or minus the standard deviation. Of course, we can use this symbol also. I'll just use it like this. So average plus or minus the standard deviation could be the range of the degree values. Again, not all the degrees values could fall in this range, but kind of roughly we can say the range of degree values for the given network would be the average plus or minus standard deviation. Okay, this is reasonable to say if the standard deviation is kind of less than the average. So again, when you computed the standard deviation, what did we do? We took k minus average degree. So the difference, right, would ideally we would like it to be 0. If all the vertices are the same degree, then the average degree will be same as the common degree, right? So which means, would there be any standard deviation if all vertices are the same degree? No. So standard deviation is a measure of variation, right? So if all vertices are the same degree, the standard deviation will be 0. So we have a non-zero standard deviation only because the vertices are different degree. So we want to quantify the extent of variation in the degree, right? So if the variation is larger, the standard deviation will be larger. Is that clear? So ideally we would like the standard deviation to be less than the average, okay? And the Poisson distribution satisfies such a relationship. So if you look at the graph here, okay, so for a Poisson distribution, the theoretical formula for standard deviation is what? Anyone can say? If this is average degree, the standard deviation is, what is the, let me use the same notation here. So I mix up notations, but they are all the same. So this is the same as average. So for a Poisson distribution, the standard deviation is square root of average degree. So in your math class sometime back, you should have seen this formula. Okay? So if I say the range of degree values is average plus or minus standard deviation, then basically the range is going to be, in this case, this plus or minus square root of this. So square root of some number, and if especially the average degree is greater than 1, is going to be what? Less than the value itself, right? So if you have something greater than 1, the square root of that number is going to be less than that number. So square root of say 4 is 2. So 2 is less than 4 and so on. Okay? So standard deviation is less than average for Poisson that clear? Okay. So if you draw the curve like this is the average, the peak is the average, and how far from the peak you have here, that is the square root of the average. So this is the average. Okay, so this is the K average. And square root of that is like what? Square root of 9.9 is going to be like 3 point something. So this is this 3.1. Okay, square root of 9.9. And this is also 3.1. So why that? Because I said plus or minus. So if you see here, this is the pK value corresponding to what? The average minus standard deviation. This is the pK value corresponding to the average plus standard deviation. So the area under this curve, so majority of the values, so you have very less area uncovered under this curve outside this range. So majority is within this range. Is that clear? So majority of the curve is within what? The average plus or minus standard deviation. So that is also a nature of Poisson distribution. Okay? So why I say all these things? Because later we'll look at what's called scale-free networks. So for scale-free networks, what's the nature of the distribution? We saw the curve earlier in the first module. It will be like this, K versus Pk. It will not be a Poisson curve like this. This is Poisson. Okay? So for scale-free networks, the curve would be like this. Okay? So for such networks, the standard deviation of the node degrees may be even greater than the average node degree. So we cannot say the range of node degree is K average plus or minus the standard deviation if the standard deviation is greater than the average. Okay, so if it's like 10 is the standard average and 100 is the standard deviation, because this formula is only for what? Poisson distribution. So don't think this formula is for every distribution model. So for scale-free networks which do not exhibit Poisson distribution, it is something like this. Okay, so this is called power law model. So there is some other kind of formula or approach to find standard deviation for power law distribution. There's no, we cannot say the degree values will be within this range because standard deviation is larger than average. Okay, so we say this is like a scale. Why is like a scale? Because the average, the range of degree values is well within the limit of what? Standard deviation. Most of the vertices have degree plus or minus the average. Whereas here, we cannot say there is such a scale. We cannot say this is a scale for the degree because the degree values could be anything. The average could be this. Okay? Whereas there are a lot of vertices with degree values far away from the average. So that is why these are called scale-free networks. Okay? So remember that. So I may not explain again that this detail when we see scale-free networks and this. Okay, so remember we'll just build on top of it later. Okay. Any question? Okay, so let me see how much time we have. Now, what do you think about the clustering coefficient for any node? Any smart answer? So what is the form? What is the clustering coefficient for a node? What does it indicate? You did that in exam 1, right? How you find the local clustering coefficient?
How the neighbors are connected.
Right. So it is the probability that any two neighbors of a node are connected. So how you find it? So given a node and its neighbors, you need to know the number of neighbors, right? So you counted the actual number of edges between the neighbors divided by what?
Total number of nodes.
The maximum possible number of edges between those neighbors, right? So you have, say, a node that we are interested at, and let us say it has, say, 4 neighbors. And let us clustering coefficient of this node, so U, is going to be what? The 4 neighbors, so the maximum possible number of links between the 4 neighbors is 4 times 4 minus 1 over 2, and the actual number of links is 2, these 2 links, right? So it will come out to be 2 over 6. Okay. So this is like what I said is the probability that any 2 neighbors of a node are connected. So that's the definition of local clustering coefficient. So local clustering coefficient of a node is the probability that any 2 neighbors of a node are connected. Now put that definition in the context of this ER model. The ER model, what is this p-link or this p-value? So again, p-link or p mean the same. So p-link is the probability that any 2 nodes in the graph are connected, right? And what is local clustering coefficient? The probability that any 2 neighbors of a node are connected, which are also nodes, right? So which means according to the ER model, okay, so if you generate a random network according to the ER model, then the local clustering coefficient for any node will be same as p-link. Okay, so the local clustering coefficient will not vary with nodes, because you may think in general, depending on the number of neighbors you have, the local clustering coefficient will vary, right? Remember I also said this. So if a node has several neighbors, isn't it? Then the chances that any 2 neighbors are connected is going to be less. Okay, so nodes with a larger degree are likely to have what? A smaller local clustering coefficient. On the other hand, if a node has a smaller degree, like on just 3 neighbors, the probability that any 2 neighbors of a node of the node are connected is going to be high, right? Because only few nodes, so there could be a link between the nodes, the neighbor nodes. Okay, so nodes with a smaller degree are likely to have a larger clustering coefficient. That is in reality, real world networks. But according to the random network model, there is no such variation of local clustering coefficient with node degree. All nodes have the same local clustering coefficient, irrespective of their node degree. Okay, so this is the relationship between local clustering coefficient and node degree according to the ER model. All nodes have the same local clustering coefficient, irrespective of the degree. Okay, or expected, not like you can guarantee it, or expected to have the same degree, same local clustering coefficient, irrespective of the node degree. Whereas you expect the local clustering coefficient to decrease with node degree. This is what in reality is. So in real world networks, you expect the local clustering coefficient to decrease with node degree. Okay. So what we are going to do next class is build on top of this. So given a real world network, we can find a metric that will say whether it is close to a random network or far away from a random network. Okay? Because we're going to basically find something like this. If the distribution of the k-basis local clustering coefficient is more or less like a straight line or flat line like this. If it's a flat line, it means what? The local clustering coefficient does not change with degree. Then it's more like a random network. It's not like a non-random network where you expect something like this. So if the local clustering coefficient decreases with degree like this, then the network is not random in nature. If the network is not random in nature, it means the links.
What you say? Repeat.
If the distribution of k versus local clustering coefficient is decreasing trend like this, then it's not a random network. The links are kind of more preferentially created. Again, random means just 2 random nodes connected to each other. Whereas if the distribution is more like a straight line like this, it means what? The real world network is more random in nature. It's a flat line. So we're going to find the slope. A flat line will have a slope of what? 0. Right? So So we'll make use of all these things and find what's called the randomness index. Okay, so next class we'll do also, this is like from real world data. You see the decreasing trend, okay? So that's for real world network.